In this module, we will explore Le Chatelier's principle and how it affects the system at chemical equilibrium. Because there are many examples to look at, we will divide this into two parts. Our objective of this unit is to understand the concept of Le Chatelier's principle and to be able to predict how different changes will affect a system at chemical equilibrium. Before we can start looking at the specific details, we need to understand the general concept of Le Chatelier's principle. And what it tells us is that when a chemical system or a chemical reaction is at equilibrium, is disturbed, the system shifts in a direction to minimize the disturbance. Well, we see this in our everyday lives if we've ever been on an elevator. If there's one person on an elevator and a second person gets on, everyone rearranges in order to spread themselves out. A third person gets on, we all move again, a fourth and a fifth, until we get to the point where we just can't move anymore, but we try to spread ourselves out on the elevator. We rarely ever see an elevator door open and find four people all standing really close together on one side of the elevator and the other being empty. As each person gets on the elevator, we're disturbing that equilibrium, and the system, which is the people already in the elevator, have to respond or shift in order to minimize that disturbance. So how do we relate Le Chatelier's principle back to the concepts we've already explored with equilibrium? Well, if we look at a room full of people, we see that all the people are in the room. Now, this system is not at equilibrium. It's got to go to equilibrium. And so to get to equilibrium, what we see is that three people leave the room. And when those three people are outside of the room, our system is now at equilibrium. Remember, equilibrium is products over reactants, or in this case, we can look at it, the ratio of the number of people outside the room compared to the number of people inside the room. So here we have a system at equilibrium. We have three people outside the room and the rest of the people inside the room. Now, as time goes on, we have different people outside the room. Here, our blue people have come back into the room and the purple people have left. We are still at equilibrium because what we're seeing is that the number of people outside the room is still 3 and the rest of the people are inside the room, and so our ratio remains the same. Now we have a system at equilibrium again, and we disturb that equilibrium in some way. We're not going to worry about what that disturbance is. Say we add some more people, we change something about the ratio, but we disturb that system at equilibrium, and what we see is that the new equilibrium is established. And so now this new equilibrium has 4 people outside of the room and the rest of the people inside the room. But the system had to respond to that disturbance to the equilibrium. Maybe we turned up the heat, maybe the music changed, maybe they ran out of food. Something changed to disturb that system that was at equilibrium, and it had to respond, and at this point, equilibrium was restored. There are many things that can affect a system at equilibrium. All of these disturbances can happen to a reaction or to some system, and the system will respond in such a way to minimize this disturbance. And so we can look at a variety of topics, and we will actually go through examples of each of these so we can see how they apply to actual chemical reactions. We can change the concentration of a reactant or a product. We can change the pressure of the system, and we can change the pressure in 2 different ways. One, by changing the volume of a container or the addition of an inert gas. Remember that inert just means unreactive. And what we'll find is that inert gas actually doesn't have any effect on the equilibrium. We can also change the temperature, and we have to worry about, is this an exothermic process where heat is being released, or is this an endothermic process where heat is being consumed? Because changes in temperature will affect those reactions in different ways. So let's look at an example here where we're looking at a reaction. We have our balanced chemical equation, carbon monoxide reacting with hydrogen to produce methanol. And what we're going to look at is we're going to change the concentration of a reactant. And so what happens if we increase the concentration of a reactant? We're going to see the formation of more products. It's going to favor the formation of products. Because if I add additional carbon monoxide, for example, now I've disturbed my equilibrium. We know that K equals concentrations of our products over the concentrations of our reactants. And if I add reactants, I now have a bigger number on the bottom than I would need to have in order to balance and have the correct ratio with the concentration of the products. What needs to happen is that some of the excess CO that was added needs to be consumed and formed into products. As a result, we will also see a reduction in the amount of H2 present because it's needed to react with the CO. We're going to see an increase in the amount of CH3OH formed because we need to form products, we need to increase the concentration of products, and we need to decrease the concentration of reactants, which we've also done. And what this will allow the system to do is to return to equilibrium, where we maintain that constant value for the equilibrium constants of products over reactants. So now what happens if I decrease the amount of a reactant? Let's say I remove some carbon monoxide. I'm not worried about the logistics or the experimental parameters or the setup that I need to be able to remove it, but the amount of CO available decreases. What happens is the concentration of our reactants decrease, and now we've disturbed this ratio. We are no longer a system at equilibrium. In order to restore the system to equilibrium, it's going to have to compensate for that lost carbon monoxide, and so as a result, the reaction is going to shift to the left or favor the formation of more reactants. Some of our CH3OH will decompose, will increase the amount of H2 a little bit, will increase the amount of CO a little bit, until we get to the point where the concentration of the products over the concentration of our reactants is equal to K. Now, at this point, we are going to have a different amount of CO, a different amount of H2, and a different amount of methanol than we originally had, but the important thing is that we return to that ratio, which is the equilibrium constant K. So let's look at a drawing here of what's going on. Here I have my reaction at equilibrium in the first panel. I go to the second panel. I've added additional carbon monoxide. Now the reaction needs to return to equilibrium. In order to do this, it needs to consume one of our carbon monoxides and two of our hydrogens. And when it does that, it will form a molecule of CH3OH. So if we look over here after equilibrium has been reestablished, we see we've increased the amount of CH3OH present. We've gone down to having 3 carbon monoxides present, and we've also lost 2 of our hydrogens because they were consumed when that carbon monoxide reacted. So now we're back at equilibrium. While we have a different number of molecules present, we're going to maintain that same ratio. Now we can look at the same reaction and see what happens when we change the concentration of a product. Since there's only one product, we'll be looking at methanol. If I increase the amount of methanol present, I see that the reaction now has too much methanol. I need to get rid of some of that methanol, and so as a result we're going to see the decomposition into carbon monoxide and hydrogen. So we're going to lose some of our CH3OH in order to get back to that equilibrium ratio. So if I increase the concentration of methanol, I see that I'm going to favor the formation of more reactants. If I decrease the amount of CH3OH present, I'd remove some of that methanol. So now looking at my equilibrium constant, K equals products over reactants, I've lost some of my methanol, and I need to make up for that loss. So I need to produce some more methanol to make up some of what I've lost. But in the process, I'm also going to decrease the amount of reactants present, and as a result, I will get back to the product-reactant ratio that is equal to the equilibrium constant K. And so for decreasing the amount of products, I'm going to favor the formation of more products. I need to compensate for that lost amount of CH3OH. Now these are just 2 examples of what Le Chatelier's principle is telling us. It's all about responding to some disturbance to the equilibrium. In these 2 scenarios, we looked at increasing and decreasing the amounts of reactants and products. We can also look at our system at equilibrium, looking at our same reaction we looked at before. Now what we're looking at is we're adding more methanol. So here we've added more methanol to the system. And what we see happening is that when an equilibrium is reestablished, I actually lose one of those methanol molecules and I actually form more carbon monoxide, and I form some more hydrogen molecules. So these are my molecules that form. And what happens is that now I've formed more of my reactants. I'm re-establishing that equilibrium by the addition of methanol. We could look at a similar idea for the removal of methanol. We would just see that the formation of our products is favored instead of the formation of reactants that's favored when we add methanol.